Hello, welcome back. The title of this lesson is called Density and Volume in Chemistry, and this is part 1. So I'm excited to teach this because volume and density come into play very early on in chemistry. And we have to understand the units of density and what they mean, and also volume and what it means. So that's what we're going to cover. But also here as well in this lesson early on, I'm going to talk about something incredibly important that I don't want to hide. It's really a problem near the end of this lesson, but I want to bring it up here in the beginning. So here is a model, what we call a ball and stick model of a water molecule. Now notice as I've been drawing these things on the board a few times in passing, I've been trying to kind of like introduce some topics to you a little bit early on that maybe aren't usually taught until a little bit later, because I think they're that critically important. This is a water molecule and it's a bent molecule. So this is the oxygen, and these two white ones are the hydrogen. So H2O. Now notice it's bent. It's not in a straight line. Now we're going to talk in great detail in the future as to why this water molecule is bent. And the reason, basically, in a nutshell, is when we talk about the electrons that are surrounding these atoms and the way in which they're shared between the atoms and they're bonded, and the leftover electrons that are also around this oxygen here, there are electrons up here that are basically pushing those hydrogens down and forming this bent shape. So you don't need to know why it's bent right now. I just need you to know that water is a bent molecule, and it's never going to go away. It's never going to be not bent. It's always like that. I don't want you to be surprised by that 5 chapters from now. I want you to know this early in the beginning. And the reason I'm bringing this up is because it's a common knowledge that when we take water and freeze it into ice, ice floats. So that actually is extremely weird. The fact that ice floats, the solid form of the substance floats on the liquid form of the substance, solid ice being solid water, floating on top of the water, that's extremely weird. And we're going to talk about why that's weird when we discuss density here. It all comes down to density. So in the course of this lesson, very soon, if you stick with me, we're going to talk about why water floats when it's frozen, and we're going to have to use these little molecular models to show that. So we're talking about density, we're talking about volume, we're going to talk about why most items, when you freeze them, they actually sink, but water, because of the bent shape of this molecule and some other features we need to talk about, water is the oddball, and it actually floats whenever you freeze it. And actually, if water didn't float, there would be no life on planet Earth at all. So the fact that this water molecule looks a little weird, bent, also the way the charges are laid out, it means that water will float when it freezes. And because of that, when we have the winters and the ice ages and all that stuff, the ice freezes on the top of the lake first, and that insulates all the body of water below to allow the fish to swim and all these things and evolution to happen. If water didn't float, then the lakes and the rivers and the streams and the oceans would freeze from the bottom up, because as the water would freeze, it would sink in that case. And then you would have no life. Everything would be just frozen solid. But because water floats, it allows the insulating layer of ice on the top of a body of water when it freezes, and then everything can still be swimming in the cold water underneath it, right? And it all comes down to the shape of this molecule and the charges and things that we're going to talk about. It's all about density. We're going to get to that very, very soon. But, I just wanted to kind of whet your little appetite there. Stick with me, we're going to get to that. Before we get to that, we need to talk about volume in the SI system. So the SI unit of length, right? The metric system unit of length, the SI system, is, as you know, a meter. And the symbol for a meter is M, right? And so volume is if you think of a meter measuring distance along a straight line, volume is measuring how much space something occupies. And how do you measure some amount of space? What we do is we use the unit of length, and we define a new unit, SI unit of volume, and we call that a meter cubed. So it's the base unit of meter, but then we cube it, we multiply it by itself. Now what does meter cubed mean? It literally means if you draw a cube here, if you literally draw a square, that's how you start by building a cube, draw a square first, and then you kind of extrude it into the board so that it has length, width, and height, right? And then you say that this side is 1 meter tall, and you say this side is 1 meter tall, and you say that this side is 1 meter tall, then we call it a cubic meter. So when we say meters cubed, The better way to read it isn't to call it meters cubed. The better way to read it is call it a cubic meter. It's literally a volume of space defined by a box where every edge of the box, every side of it, is just 1 meter long. That's a cubic meter. Now, the base unit of volume in the metric system or the SI system is a cubic meter because the base unit of length is a meter. But that doesn't mean we always have to use cubic meters. We can use other units of volume as well. We can also use, drum roll please, we can use a cubic centimeter, right? We can use a cubic centimeter. We can even use a cubic millimeter. In fact, we can use a cubic light year if we want to for distance. We can use a cubic kilometer if we want to, but we really have no use for those, especially in chemistry. We're measuring things in the laboratory. Usually they're small things we're putting in a test tube. It's going to be cubic millimeter, cubic centimeter for volumes. Even a cubic meter is a huge volume. It's a box this wide and this tall and this deep. It's a lot of volume, a cubic meter. So it's a little bit too big of a unit, even though it is the base unit. So we usually use cubic centimeters or cubic millimeters in chemistry. Now I also need to point out something. Note something very important, right? You all have gone to the store and purchased a liter of water, or maybe a 2 liter of a drink or something like this. So the unit of a liter is something we have everyday experience with, where we purchase and we measure things in liters all the time. How does a liter fit into this? Because a liter is also a measure of volume. Here is the connection between liters and what I've said up here before. 1 cubic centimeter, which by the way, is a cube. Instead of being a meter on each side, it would be 1 centimeter deep and 1 centimeter long and 1 centimeter high. That's like the size of a sugar cube or so, is a cubic centimeter. 1 cubic centimeter is exactly equal by definition to be what we call 1 milliliter. And I know that you've heard of the term milliliter. And 1 liter is equal to 1,000 of these very small milliliter. 1 liter is equal to 1,000 of these very small milliliters. So this is the connection between liters and the base units here. So basically, you can often find volume expressed in chemistry in terms of cubic centimeters. But because a cubic centimeter, the size of this, little, I guess 1 centimeter on each side, like this, because 1 cubic centimeter is exactly the same volume as 1 milliliter, that's the connection. And because there are 1,000 of these milliliters in a liter, that's how you get from the base unit being cubic meters, we can go to cubic centimeters, and then we know 1 cubic centimeter is equal to 1 milliliter. I want you to remember that because sometimes when people talk about volume, they'll express it in cubic centimeters, and sometimes they'll say they'll just say milliliters, and you have to know that a milliliter is exactly the same thing as a cubic centimeter. So it's very important for you to remember this, and over time you'll start to remember this in your mind. Now all of these units I've written down here, the milliliters, the liters, the cubic centimeters and all that, they're called derived units. Because really the base unit of length is a meter. The length is the base unit. We're deriving other units in terms like volume and things like this because we're basically taking that base unit and doing something else with it. There are other derived units that we're going to talk about. Probably the easiest to understand derived unit is speed, meters per second. You take an SI unit of length, meter, an SI unit of second, divide them, and you get a new unit that we use very, very often. So meters per second, or gravitational acceleration, meters per second squared, right? Those are all derived units because they come from the base units. So next we have to talk about one of the most important derived units in chemistry, and that is called the density of a substance. A density. So this is how it's going to tie into the density in our discussion of water like we just talked about. So the density of an object is equal to the mass of the object, and we're going to talk about all this, divided by the volume of the object, right? So it's a derived unit because we take a unit of mass, which is one of the core units of the SI system, and a unit of volume, which is again coming from the length, but it's coming from meters, or cubic meters, cubic centimeters. And we're creating a new unit by taking the mass and dividing it by the volume. So it's a derived unit. Why do we care about density? So density is a measure of not only how much mass something has, but how much space that object occupies. So it takes both into account, because you could have a truck full of cotton, right, that has a certain mass, or you could take that cotton and you could compress it down into a small size. It would have the same mass, but you could compress it because it's very compressible into a smaller size. So if you take some object that has a fixed amount of kilograms of mass and compress it, the mass of the object will stay the same, but because it's now occupying a smaller space, the density has changed. Because the density is the mass of the object divided by the total volume of the object. So what units do we really use or usually use in chemistry? Well, we can use, if we want to, kilograms for the mass and cubic meters for the volume, because we just said that the base unit is kilograms for mass in the last lesson, and cubic meters is the base unit for volume, or the SI unit there. The problem is kilogram is a large amount of stuff, of mass, and cubic meter is an enormous volume. So when we're in the laboratory, measuring it in that system is just too big. So we don't really do that. What we normally really use is we use grams, which is a much smaller unit. That's 1,000 times smaller than kilograms, right? And we use cubic centimeters, because a cubic centimeter is also a small amount. And you can also use grams per milliliter. Now, what is the difference between grams per cubic centimeter and grams per milliliter? Remember, we just said that 1 cubic centimeter is exactly the same thing as 1 milliliter. So if you see the density of something represented in grams per cubic centimeter, and you see some other label measured in grams per milliliter, these are the same thing, because a cubic centimeter and a milliliter are the same. I keep saying it over and over again because sometimes you will see it expressed different ways, different textbooks, sometimes even different formulas may have the units different, but a milliliter is the same thing as a cubic centimeter. I want you to try to remember that. So most things I don't ask you to remember because we can use the periodic table or look it up in a book, but I want you to try to remember that, okay? Now let's talk about conceptually the idea of density again. Let's say I have that giant amount of cotton, as I mentioned a second ago. Let's say it's occupying this much space, and it has a certain amount of mass. And then what I do is I compress it. I put it in a compactor and I compress it on all sides, but notice it has the same mass. Because the mass is basically a measurement of how many atoms are in something and also the type of atom. You know, an iron atom has a higher mass than a nitrogen atom. So when you measure the amount of kilograms in something or the amount of grams in something, the mass of something, it's taking into account how many atoms or molecules there are and what type there are, because you know atoms or molecules have different intrinsic masses because of the protons and things that are in there. So it's a total measurement, the mass is, of the amount of the substance you have, how much of it exists in front of you there. But if you take this cotton and you compress it, it has the same mass after you compress it, but after the compression, it's going to have a much smaller volume, right? So notice that density is mass divided by volume. So what do you think is going to happen if this has a certain mass and you divide it by the volume of this, or whatever the volume of this thing is? You take its mass, you divide it by the volume. You're going to get something called density, right? The units of the density might be grams per cubic centimeter, or we could call it grams per milliliter. What's going to happen when you compress it down? Well, it's going to be the same amount of grams, because when you compress something, it doesn't change how much mass is there, but the volume will be smaller. That means the denominator here will go down. And when you divide things, if you make the denominator smaller, then when you do the division, it makes the density go up. So as you compress it, what's happening is the mass is the same, but because the volume is different, the density is getting higher and higher. So let's just say, for instance, that we look over here at this cotton and we actually carve out, we just get a knife and we cut 1 cubic centimeter out of this thing. So how would you do it? You would literally carve out an exact cube, 1 centimeter on each side. And let's say that it's, I don't know, when you cut that thing out and you figure out how much mass is in there, you figure out it was 2 grams per cubic centimeter. You cut out a cubic centimeter and figure out how much mass is in there and it comes out to 2 grams. Now you go over here after it's compressed and you do the same thing. You get a knife out and you literally just cut it like this. And you cut out a cubic centimeter here. Right? Well, you have to have an intuitive idea. Don't calculate anything. Is the density going to be higher or lower? Well, you've compressed this stuff. So if you cut the same volume, you're grabbing more mass because you've literally crammed the mass into a smaller place. So when you pull that thing out, it might say something like 10 grams per cubic centimeter. And you see the density went up for the same reason I explained to you a minute ago. The mass stays the same. When you compress it down, the volume gets smaller, so you divide, and the density goes up. So if you cut 1 cubic centimeter out of each of these things and measure the mass, then of course you have a higher mass for the same cubic centimeter. We say that this is a higher density, and we say that this one is a lower density. I want you to get an intuitive understanding. We're going to calculate density for a lot of problems here in a second. We're going to find mass and volume, divide, calculate, and you're just going to get numbers and numbers and numbers and numbers. But I want you to get an intuitive feel. I want you to understand the equations instead of just cranking through the calculation. When you divide a mass divided by volume, it is a ratio of how much amount of stuff you have compared to how much space it takes up. If you compress it, then it takes up less space. The density must go up because it's a measure of how much mass exists in every single cubic centimeter or milliliter, same thing, in those spaces. Now, let's get to the exciting part of the lesson, I think anyway. All right, the density of water, H2O, is equal to 1 gram per milliliter at 4 degrees Celsius. Now, actually, it's not exactly 1 gram per milliliter. It's very, very close. It's like 0.9999 and then some numbers, grams per milliliter, which remember, grams per milliliter is exactly the same thing as grams per cubic centimeter. I'm trying to reinforce this. These are the same units. They just look different. Now, we express it at 4 degrees Celsius. Why? Because from physics, we know that if we heat things up or cool things down, they get bigger or smaller. So we have to specify, or in textbooks and in real life, we always specify the density of something at a certain temperature, because if I take, a block of lead or a block of copper or whatever it is, and I heat it up, it's going to get bigger. And then the volume changes, so the density changes. So because I need to know, I have to compare things, in a similar fashion, I need to specify the temperature. So the density of water is at 4 degrees Celsius, this number here. Now here is the punchline. How do we know if an object will float on water? An object will float on water or in any liquid, right? If its density is greater than 1 gram per milliliter, because that's the liquid I'm talking about, water. If sorry, I did that the wrong way. If its density is less than 1 gram per milliliter, and it will sink. It will sink if the density is greater than 1 gram per milliliter or 1 gram per cubic centimeter, however you want to specify it. Now, I could go in, if this were a physics class, we could actually prove why that's the case. It comes down to what the buoyant force is. Why do things float? That's a physics lesson for a different day. But the way it works out is if you know the density of the liquid you're talking about, and you know the density of what you plan to drop into the liquid, all you do is compare the densities. If the density is more than the density of the liquid you're trying to float in, if it's higher than that, it's going to sink like a rock. The density of a rock is bigger than water, it sinks. The density of, of metal, like, lead or something, is more than water, so it sinks. But things that float on water, the density has to be less than the water. So wood, most types of wood, the density is less than water, so it floats. The density of, very light plastic or something like this is less than the density of water, so it floats. So here brings us back to the beginning of the lesson. If density is mass divided by volume, what happens to most things when we cool it down? Let's take some other liquid, just some other fictitious liquid, just make up another liquid. It could be, I don't know, some other hydrocarbon, gasoline. We could talk about lots of liquids, but let's just make up a fictitious liquid in our mind and let's cool it down. So what happens when we freeze most things? The molecular motion slows down, slows down, slows down, slows. They're bouncing off each other in the liquid state. We cool them down, They're bouncing less and less and less vigorously. Eventually they sort of stop moving and they settle into kind of a fixed state. So what's happening is because they're not moving very much, most things contract when they get colder. That means the volume goes down. So if the volume of something goes down when they get to be a solid, the density actually goes up, right? The density gets higher. Let me repeat that. Most objects, like pretty much anything you could think of, right? If you cool things down to make them a solid, the volume goes down. And if the volume goes down, the density goes up. And if the density goes up, it sinks. So that means that water is a real oddball situation because most other liquids like methane or whatever else you want to talk about, if You cool it down into a solid form, it contracts so that, and the density goes up. And because the density goes up, it sinks to the bottom like that. So that bears repeating because it's so important for you to understand. Most other liquids, methane, other liquids that you could go purchase somewhere or just find in the universe, when you cool them down and they form a solid, the solid form sinks to the bottom. So if you had a pool of methane here and you started cooling it down, the parts on the top that became solid will just sink to the bottom. And then they'll collect on the bottom like rocks. And then the next layer on the top will sink again and sink again. So what happens is the river or the lake, it will start to freeze from the bottom up. And if things stay cold for long enough, you have a solid frozen river. I mean, it won't even be flowing anymore. But we all know that ice doesn't do that. When lakes and rivers freeze, they freeze from the top. When you take an ice cube and you put it into the liquid water, it floats, it doesn't sink. And that is extremely, not only weird behavior, but it's incredibly fortunate that that happens because ice does not sink when it freezes, it floats. What happens is, as soon as a thin layer of ice forms on the top of a river, ice is also a good insulator and it prevents the rest of the body of water from getting as cold as fast. Of course, you could still freeze a cup of water solid. But if you have a very thick river and it doesn't get too cold, what will happen is the top will freeze and it will sort of insulate the bottom because it's floating on the top. It will insulate the body of water below from freezing. It'll take longer to freeze, basically. And if it doesn't get cold enough, the bottom won't freeze at all. That means all the fishes and everything else going on there can continue to, over millions of years evolve into us. So because ice floats, we have been able to essentially have the chemistry going on in the oceans for millions, billions of years, leading to life. If ice did not float, if ice sank to the bottom, and all of the rivers and streams and oceans froze from the bottom up, then there would be no life. So it's incredibly, not only interesting, but incredibly fortunate that ice actually floats. Now, let's get to the punchline. We're going to talk about this a lot later because we're going to have entire chapters on, what water does when it freezes. But since it's such a cool thing, I want to show you real quick, and it's very easy to understand. So here's water molecule number 1, and here's water molecule number 2. Oxygen and 2 hydrogens. Oxygen and 2 hydrogens. It's a bent molecule. It's a bent molecule. The reason they're bent molecules is because there are extra electrons up here that I haven't put any sticks on that are there, and they're pushing the hydrogens down into a bent shape. Why are those extra electrons there? We'll get to it. It comes down to how the electrons are going around these oxygen atoms. So we have these bent molecules. Now what's happening is in the liquid phase, these things are colliding with each other, flowing around. Notice they're bent. They can kind of get pretty close to each other before bouncing off. They can get very intimate with each other and kind of mix and intertwine with each other like this. Now let me pause here and remind you of something that I told you a few lessons ago. I told you I would be drawing it over and over and over again. Again, we're going to get to this stuff a lot later. But when we draw the H2O molecule, we don't draw it in a straight line, we draw it as a bent molecule. So here is H2O, H2O, okay? Now we're gonna learn later, much later, we're gonna learn that oxygen is very, very attractive of electrons. See, the elements on the periodic table, they don't all attract electrons with the same strength. It all comes down to the electric force. We're going to talk about the electric force later, but for now, just know that different elements on the table have different attractive strength to try to pull electrons in. And it turns out that oxygen is one of the strongest elements to attract electrons. So this bond from oxygen to hydrogen to hold the molecule together, this bond is a sharing of electrons. The electron around the hydrogen and one of the electrons around the oxygen, they're basically shared with each other, and that's what this line and this line represents. But since oxygen is such strength in attracting electrons, it turns out that these pair of electrons that are here are shifted more towards the oxygen just a tiny bit. And that means that over around the oxygen, there is a very slight negative charge compared to around the hydrogen. Now, don't get so worried about this little Greek delta here. This is a Greek delta. It's just a symbol. It doesn't actually have any meaning. I'm just putting it there to tell you that this hydrogen is very slightly positive because the electrons were very slightly pulled towards the oxygen. This hydrogen is also very slightly pulled because you would think they would be sharing these electrons exactly in the middle, even. But really it's not. They're pulled towards the oxygen. So there's a slight positive charge. Why? Because hydrogen has a proton in the middle. So if you suck the electron a little farther away from it, it's going to, when you zoom in on it, be a little more positive, and the oxygen will be a little more negative because it's pulling the electrons a little closer. We call that polar. We call this idea that H2O is a polar molecule. Now, there are other molecules that are polar, but water is the most common, one of the most common things on the planet, and we drink it, and we're mostly made of water, so it's probably worth a few minutes of your time to understand how water is built. It's one oxygen atom, it's two hydrogen atoms, this line represents electron sharing, and this line represents electron sharing, and that's bonded together. That's what a bond is when we share electrons. We're going to talk about that a lot more later. But the sharing isn't really equal. Oxygen is stronger, so it pulls the electrons very slightly closer to it on both sides, and therefore we have a little bit of a positive charge on the hydrogens and a little bit of an extra negative charge on the oxygen. Now, that is the secret sauce to understanding all of this stuff when it comes to ice, because here's two water molecules. This is the oxygen. This is the oxygen. The white ones are the hydrogen. The white ones are the hydrogen. And we just said that the oxygen here, the red one, has a slight negative charge, very slight. This oxygen also has a very slight negative charge. The white ones here, very slight positive charge. So in the liquid phase, the water is just bouncing off and it's got a lot of thermal motion. So things are moving real rapidly. They're able to notice how they can curl around the other guy here. And just that's how water flows because the molecules can get very close and mix. But now we start to cool it down. The motion starts to slow down. What is going to happen if you put two of these molecules next to each other? Well, the hydrogens are positive and the oxygens are negative. Opposites attract. I'll say that again. Opposites attract and like repels. So if I have two water molecules like this and they get close to each other like this, well, the white balls here are very slightly positive. They're going to repel each other and they're going to bounce off the other way. But eventually, through random chance, what's going to happen is that this hydrogen, which is very slightly positive, is going to come near one of the oxygen atoms of another molecule, and it's going to want to stick because they're attractive. So you see what's happening here? You have this guy that's going to, and once we cool it down so that there's not much motion going on, they're going to lock into place like this because the positive and the negative are attracting each other. And so it stays like this. And then on the other side, you're going to have another water molecule. Once it finally settles in place, it's going to do this. You see what's happening? It's forming a lattice. And because in the liquid phase, things can mix and get real close together, now everything is forced to stay farther apart because of this attractive lattice that forms. So why does water or ice float? It's because when you cool things down, the attractive force between the hydrogen and the oxygen of an adjacent molecule, they lock it into place into a larger volume than in the liquid phase. Because it's locked in place like this, it has to be a larger volume overall than in the liquid phase. And if the volume is larger, then the density goes down. If you put a bigger number in the bottom, for the volume, you divide by a bigger number, you get a smaller density than water. And a smaller density of water means that it floats. So it comes down to two things. Water is a bent molecule. If it wasn't bent, it wouldn't quite do this. And the reason it's bent, we'll talk about later. And it is also possible, it behaves this way, because water is polar. Because this oxygen has a very slight negative charge on it, and all the white hydrogens have a very slight positive charge on it. So once they stop crashing around, they get slower and slower and slower. This electric force takes over, and then they get stuck together like this. And this pattern, this lattice pattern repeats, and ice has a larger volume than liquid water. And because of that, the density goes down, and so because of that, it floats. So that is something that we're going to talk a lot about later, of course, when we talk about molecular shapes and things like that, but I just can't resist because we're talking about density, we're talking about water. One of the problems even involves the density of water. So I didn't want to pass up the opportunity to show you something which, to be quite honest with you, is one of the most important things for life on this planet. So you literally know something that people didn't know a few hundred years ago, and it is absolutely critical for life to form on this planet. All right, now believe it or not, that was just the introduction. I kind of went on a kind of an aside with the density of water. If you don't quite get it, we'll get to it a little bit later. I'll show you some pictures of water ice and we'll talk about it. But I want you to know water is bent, water is polar. I want you to know that in the very beginning because it affects everything. But the critical thing here is to know what density is. Mass divided by volume. Here we're going to solve our first problem. And it says, A penny with a mass of 2.490 grams has a volume of 0.3490 centimeters. Calculate the density and explain how you would determine if the penny was made of pure copper. So let's tackle the first part of it, calculate the density. Well, the problem says that the mass of this sample is 2.490 grams, and the volume is 0.3490 cubic centimeters. So how do we find the density? The density is always the same equation. The density is equal to the mass over the volume. So the density is equal to the mass, this number, 2.490, and that's in grams, given in grams here, and the volume is given as 0.3490, and that's in cubic centimeters. So you can see that the unit we get is going to be grams per cubic centimeter. So if we take 2.490, divide by 0.3490, we get a density of 7.135 grams per cubic centimeter. 7.135 grams per cubic centimeter. So that's the density of the copper now, or the density of the penny that we have. How do we determine if it's pure copper? Well, we go into a reference book or a chemistry book or somewhere on the web, and we go look up a value for the density of pure copper. How many grams per cubic centimeter pure copper is, and we compare it to what we got for the penny. So this is for the penny. And when you actually look that up, the density of copper turns out to be 8.96 grams per cubic centimeter. Now, it's important you have to have the same units in order to compare these. And you can see that 8.96 grams per cubic centimeter is nowhere close to this density, so not pure. It's not pure copper. We can just tell because the densities are too different. So what they did is they took some copper, which has more mass per cubic centimeter, and they dilute it down with some other cheaper metals. And they make pennies out of it, and only part of it is copper, and the other part of it is something else. So that's how we figure that out. All right, let's tackle problem number 2. It's kind of a long problem. It has a couple of different parts, so we'll tackle one part at a time. The first part says, a sample of a chemical called tetrachloroethylene has a mass of 40.550 grams and a volume of 25.00 milliliters at 25 Celsius. Notice they give the temperature. Not that we're going to do anything with it, but it's a good practice to give mass, volume, density at a certain temperature, because I told you volume changes depending on the temperature of the room, basically, that you're in. Use this information to determine the density of tetrachloroethylene and whether or not it will float on water. And then we have a part B we'll do after that. So what we want to do is calculate the density, and then we already know how to determine if something floats. We have to see if it's a larger or smaller density, bigger or smaller than the density of water. That will tell us if it floats. So in this problem, part A, we are told that the mass is 40.550 grams. And we're told that the volume is 25.00 milliliters. And we're told the temperature there. So how do we determine the density? The density is always equal to the mass divided by the volume. And the mass is 40.550, and that's in grams. And the volume is 25.00, and that's in milliliters. So when we take these numbers and divide them, the density here, just write it right here. The density here, 40.550 grams, 25 milliliters. You divide them, you get 1.622 grams per milliliter. Grams per milliliter. This is how much of this substance, how many grams of it exist in 1 milliliter of the liquid there. Now, how do we know if it's going to float or sink? Well, first of all, I want to remind you that this was expressed in grams per milliliter. But that's the same exact thing as grams per cubic centimeter. It's exactly the same unit, 1.622 grams per cubic centimeter, because a cubic centimeter is the same as a milliliter. These two numbers in units are exactly the same thing. Now, we said a minute ago that the density of water is 1 gram per milliliter or 1 gram per cubic centimeter. It's the same thing. So the density of H2O is equal to 1.00 grams per cubic centimeter. I told you this is kind of a rounded number. The real number is like 0.999 or something like this, but everybody always uses 1 gram per cubic centimeter. So because this number is bigger than this number, this stuff is going to sink. So it will sink. And it will sink because the density of that substance is greater than that of water. If the density came out to be less than that of the density of water, then it would float. All right? So that one sinks. Let's take a look at part B. It says carbon dioxide has a formula called CO2, and it's a gas at room temperature. You know that because you breathe carbon dioxide. If the pressure is raised, CO2 becomes something called a supercritical fluid with a density of 0.4690 grams per cubic centimeter. How much mass does a 25 milliliter sample of supercritical CO2 contain? Now, this problem is the first time where I think a lot of students will get confused right off the bat, because we're talking about density, and we do mention density in the problem, but I'm not asking you to calculate the density. So you're like, what do I do? What you need to do is write down what you know, and then figure out how to get where you're trying to go. So we know that whatever this stuff is, carbon dioxide is what we're talking about. The density of this is, let me read it here, 0.4690, and it's grams per cubic centimeter. All right, and we know what we're trying to examine a volume of 25 milliliters, and we're asking what's the missing part of this. We're asking how much mass is that. So let's read it again. If the pressure is raised, they're going to put a bunch of words around this problem. It doesn't make any supercritical fluid. Who cares? What it's telling you is there's a density. The density is given here. How much mass does a 25 milliliter sample contain? So you have to figure this out. Now you know that the density is equal to the mass over the volume. So if you want to solve for mass, how do you solve for mass? Well, you're going to use algebra. You multiply by the volume, by the volume, and these cancel. So the mass is equal to the density times the volume, or the volume times the density, same thing. So we can take density times volume and solve for mass. But I want to show you, and so we're going to end up multiplying these numbers together. But there's a problem, because this is in cubic centimeters, and this is in milliliters, and you have to have compatible units. But then you remember, wait a minute, this is really the same thing, because this is 0.4690 grams per milliliter, because a cubic centimeter is the same as a milliliter, and these now match. So we can then proceed. So it looks like it's a problem, but it's not, and you have to know that those are the same. So let me show you literally one of the most powerful things you will learn in all of chemistry, in all of physics, in all of math, in all of engineering. And we've talked about dimensional analysis and things in passing, but now we're going to use it here, because if I take if I don't even do this stuff, and if I don't even know I have to multiply, let's say I don't even know this, if I just write this unit down, 0.4690 grams, and I write it as a unit per milliliter. Notice I just write it as grams per milliliter, 0.4690 grams per milliliter. And then I know that I'm after a 25 milliliter sample. I can put the 25 milliliters on the bottom, but nothing will cancel. If I put the 25 milliliters on the top, then I have a cancellation of units, because units on the bottom and the top, they cancel. And so if I perform this calculation by multiplying, the only unit I have left is grams. And that's what the problem's asking for. How much mass does a 25 milliliter sample have? So even if you don't know the formula for density, even if you're not sure if you should multiply or divide, even if you don't do the algebra to figure out, we just said we have to multiply them. But even if you don't do that, if you just write the unit of density down, you know you have to multiply, because that's the only way to get a unit of mass out of it. So you take 0.4690 and you multiply by 25, and what you're going to get is, whoops, that isn't writing. You're going to get a mass of 11.73. And what unit? The only unit that's left, grams. 11.73 grams. And that's the final answer. So that is all for this lesson. We have another lesson that follows this one to do more density problems. But we have covered a tremendous amount in this lesson. We have talked about the idea that the SI unit of length is called a meter, and that's a pure unit because it's just a single dimension. It's called length, but we can create other units from the base units. One of them is called volume, cubic meters. or we could use cubic centimeters or cubic meters. And then we said that 1 cubic centimeter is the same as 1 milliliter, and we've already seen how useful that is to know. And we also know that 1,000 of these tiny milliliters are in one of these liters that you buy and you drink. So these are all important units of volume. Then we said if you take the mass of a substance and divide by its volume, you get a new unit called a density. You could express it in kilograms per cubic meter, but those are very big units, so we don't use that. We use grams per cubic centimeter or grams per milliliter most of the time because these are the same thing. We just said these are the same thing. And so intuitively, if we take a mass of something, maybe it has this much density, and we compress it, it retains the same mass, but the volume is smaller. So because the volume goes down, we divide by a smaller number, the density goes up. So it might go from, for instance, 2 grams per cubic centimeter to maybe something like 10 grams per cubic centimeter. We talked about that. Then we talked about the density of water, and we said things can float or sink on water depending on if the density is either less or greater than. If it's less than water, it'll float. If it's greater than water, it'll sink. And that holds for any liquid. You could figure out if something will float on liquid methane if you want to by comparing it to the density of liquid methane. And then we went into this side talk about water. And the idea that water is a bent molecule, and we're going to talk later about it, but really because there's extra electrons up here that push the hydrogens down into a bent shape. And then we said oxygen is one of the strong attractors of electrons. We're going to talk about that a lot more later. So the electron sharing that's happening here, which we're going to talk about later, it pulls a little bit more. And so oxygen is very slightly negative in a water molecule, and the hydrogens are very slightly positive in a water molecule. And because of that, when we cool water down, and it gets slow enough so that the positive hydrogen attracts the adjacent molecule's negative oxygen, they lock into a lattice that makes the volume of ice actually bigger than the volume of water of the same mass, and so it floats because the density goes down, right? The density goes down. And that's extremely weird. That doesn't happen to very many other substances. Certainly common things that you would do, as soon as you start cooling them down and they freeze, they're going to sink. And because of that, life forms on the planet. And then the rest of the lesson was all about just calculating density and getting some practice with it. So I'd like you to go through this a couple of times. I put a lot of thought into how to present this, and introducing these things a little early, I know it might lose some people in the beginning. But if only thing you get out of it is, okay, there's this thing called density, we calculate it, and water's a bent molecule, and it's kind of an unbalanced charge on the water, that's okay. That's all I want you to remember, because in a few chapters, we're going to dig very deep into that, and I want it to be familiar to you. Now, follow me on to the next lesson. We'll continue to work problems and build skills related to density in chemistry.